讲到 section 5嘛 ，OK, we finished section 5 last time, right? Okay, and so this chapter we have one additional section to go, and then we'll move on to the next chapter. And one more thing to remind you, okay, we have like a quiz 5 today, right? Okay, we have quiz 5 today. Okay. 好，那 let's start. Okay. So, yeah, there's a very famous theorem, okay, that we will introduce in this section. It's called Gram-Schmidt, okay, orthonormalization process, okay. Actually, this thing, we already talked about this last section, okay. Basically, okay, if you have a basis, okay, with n vectors, okay, for a vector space V, okay, and we can, sort of construct a orthogonal basis out of this basis B, okay. Basically, we let the W1, okay, the first vector in the orthogonal basis to be the V1, and the W2 we just try to get rid of the projection, okay, of W1 on V2 on W1, okay, and then okay W3 we just try to get rid of the projection of V3 on W1 and W2 and so on, okay. So by doing so, we can construct like n vectors that, each pair of them are orthogonal, and they obviously form a basis for the same vector space, okay. So yeah, I think we talked about this last time already, okay. So what's new in this section? Okay, it's just obviously. Once you have an orthogonal basis, you can create an orthonormal basis, right? Basically, okay, you just let the ui to be wi divided by the length of wi, then you get the orthonormal basis. And basically, okay, if you do that, okay, then okay, for any I, okay, in this, basically the VI, okay, this projection of the projection of VI onto the space spanned by VI to VI minus 1 is exactly the process this part we are getting rid of. This is like the V2, we are getting rid of the projection of V2 on the direction of V1, right? W1 is pretty much V1, right? And then for this part, we are trying to get rid of like the projection of V3 on the W1 and W2 and so on. So we are, for example, for VI, we are getting rid of the projection of to create WI, okay, we need to get rid of the projection of VI on the space spanned by the previous vectors, okay. Of course, the way to use it is slightly different, because now we, instead of we use WI's But in here we are using what should I say? Like yeah, it's the same thing. Okay, so basically, okay, so it will be this part. This part is exactly what we have here, right? This is the projection of Vn, okay, on the space spanned by W1, W2, W3, and so on to Wn minus 1. Okay, so this is exactly what we have in the previous one. Okay, so we basically, you know, denote this one as projection, okay, Vi on the span V1 to Vi minus 1. This is slightly different, okay, but this basically they are the same. Okay, this can be done by, we can rationalize by the injection because V1 is W1, right? The V1 is W1. Okay, and for the space spanned by V1 and V2, basically it's the space spanned by the W1, W2, and so on. So you can do like this by a very simple induction. The span of this equal to the span of this. Okay, which will be exactly this one. Okay. So here, okay, we are trying to show an example, okay, a non-trivial example, okay. This example is because here we are trying to carry over whatever we have in a vector space, in a n-dimensional vector space into like something that is not like the space that we usually consider. So this is like the Pn vector space. Okay, so that Vx1 to be -1, x2 to be 0, x3 to be 1. Okay, find orthonormal basis for P2 if the inner product on P2 is defined like this. Of course, like for each vector space, you could have a different definition of like a inner product. Okay, so this one is pretty much like just, what should I say? Like you just do like an inner product of like the xi. Just multiply xi and the qi, pxi and the qxi, and add them together. Okay, so this is very simple one because we have x1 like this, x2 like this, x3 like this. Okay, so then let's consider, okay, the basis, okay, of this vector space, okay, the P2, because P2 is like all the polynomial up to the order 2, right? So it's its easiest basis will be, V1 to be 1, V2 to be x, V3 to be x squared. Okay, that's like the easiest basis for P2, okay? And then, okay, for W1, okay, we just let it to be 1, okay? Because this is like, what we have, like here, okay, here. We just try to apply this like process. Okay, and then W2 will be V2. Okay, V2 is like x minus, okay, the inner product of like we just follow this formula. Okay, get rid of projection getting rid of this projection Vi on the projection of the previous vector space. So that's like this one. That gives us X. Okay, because the nominator is 0. Okay, so the result is X. So W2 will be this one. Okay, the length of W2 will be this one. So we need to, in order to get the U2, which I forgot to mention, we have W1, but we also need to get a U1. So it will be W1 divided by the length of W1, which is like this one. It will be 1 over square root of 3. This one is similar. We get like a length of W2, so it's going to be 1 over square root of 2 multiply X. So W3, okay, we follow a similar process. We can get U3 to be this one. Okay, so in the exam, if I give you a vector space, okay, and I give you a definition of like inner product, you should be able to do and of course, if I give you a set of like vectors as the basis, you should be able to derive a set of either orthogonal or orthonormal basis, okay, from the basis, the original basis I gave you, okay. So this is something you need to know, okay, in this section, okay. From this example, of course. So you may ask, we already know this thing in the previous section. Okay, why do we need to learn, go over the same material again with just additional examples? Okay, it is because, okay, we could sort of what should I say, put it into matrix. Okay, we can sort of represent this as a matrix. So let's have a look at this theorem. Okay, let's say B is a basis, okay, for inner product vector space V. Okay, and that B prime to be, okay, this one. Okay, this B prime basis obviously is orthonormal. Okay, you can see that. We get W1 like from V1, and then we divided the W1 by its length to get the U1, and so on. So you see W1 to Wn, these vectors are orthogonal. Okay, and then we divide. We try to divide like each Wi by its length, so they became orthonormal. So B prime is an orthonormal basis for V. So yeah, we already know this process. Then, okay, the thing is that we could represent this whole process by matrix manipulation. Okay, so if A is a n times n matrix of rank n, then A can be factored into product QR, where Q is an n times n matrix with orthonormal column vectors, and R is an upper triangle n times n matrix whose diagonal entries are all positive. So, what exactly are we talking about? Okay. So here, okay. Sorry. Okay, this is much better. So here, okay, what we have is so this is like a m times n matrices. So we have n rows. We have n rows, n columns. Right? This is the original matrix. Okay, this is A. This is A. And here I'm telling you, this is the rank n, right? This is rank n. So if you try to consider this matrix as a collection of n column vectors, so treat each one of these as a column vector. You have n column vectors, right? Because the rank is n, so that means all these column vectors form a basis, or put it another way, they are independent, right? They are independent. So far so good, right? So if they are independent, so if you try to derive an also normal basis out of these column vectors, what are you going to get? So let's follow. This is let's follow the notation. So this is A1. A1. This is A2. This is AN. Okay, and then okay. We can sort of, we know like in the previous page, we already know these notations, right? So if you want to get for example, W1, this is W1, this is W2. This is Wn. Okay. If you want this Wi to, if you want to obtain this Wi from the A1 to An, okay, here I mean they are again column vectors from A1 to An, okay, and they are orthogonal. We know W1 will be A1, right? And the W2 will be blah, 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 blah. Right? We have that, right? We have that, the only change we need to make is that we now make V1, V2, V3, Vn to be A1, A2 up to An, right? All the other part remains the same, right? Right? So, it's actually what no, it should be W1. Yeah. It'll be should be W1 minus let me double check. QR. So Q is yeah, R is upper triangle. Yeah, this one. Our Q actually is actually A. Okay. In other words, this is A1, A2, AN. Okay. And then look at here. If you have the first one, the first column to be 1, 0, 0, 0, okay, then the A1 will be your W1, right? A1 will be your W1. Okay. I mean, you can, when you do a matrix multiplication, this column, the first column is actually the first, this matrix multiplied by the first column of the second matrix. You know that, right? So this one multiplied this one, you get this one, right? Where each of these indicate like the coefficient you have for this column vectors. So because like the first one, W1 equal to V1, right? So you have a 1 here. All the other will be 0. Okay, and the W2 will be V2 minus blah, blah, blah. Okay, so we know like, okay, the coefficient for the second column will be 1. And you have something here. This is like a negative. It'll be something like here. Okay, but it's fine. I mean, or pretty. Let's use even. You can see that. Okay. You can put something here. And W3 will be, okay, the V3 minus something, right? That something comes from the first two vectors. Because like, I mean, basically, I mean, that's like a projection of V3 onto whatever vector space spanned by the previous two vectors. And so on. So basically, you will have like a 1, okay, all over the diagonal. And on top, you have something. But at the bottom, okay, below the diagonal, I mean, they are all zeros. Okay, if you try to represent this thing into the matrix multiplication, because you know you are getting basically like it's like the VI getting rid of whatever you have from the V1 to VI minus 1. So the VI guarantee like a 1 at a diagonal position, and then the other part comes from the upper part. Okay, and all the stuff below will be 0. So here, okay, this is W1 to Wn. And if you want, if you look closer, okay, here, okay, we say this the diagonal entries are all positive, okay, and we say this M times M matrix with orthonormal column. But you say, wait a moment. Let me see. Q is I think I'm getting something. Yeah, I'm doing something wrong. Okay, sorry. It should be opposite. Okay. V1 to be W1. V2, okay, we need to move this part to the other side. So, my bad. But still, I mean, the basic idea remains the same. The only difference is that, okay, we are changing this one to A1, A2, AN, and we are changing this one to W1, WN. The only difference is that, okay, we move this, minus this projection part to the other side. Okay, the other, arguments remains the same. Okay, so we still get this upper triangular matrix. Okay, as your R. So this is your Q. And this is your A. Okay? But you may argue, okay, this Q there, like, because it's W1 to Wn, they are, not, their column vectors are not orthonormal. They are orthogonal only. So what we can do is that, okay, because here in this theorem, okay, we say Q is an n times n matrix with orthonormal column vectors. So we need to do something more, okay? Basically, we need to divide this one by the length of W1, and we divide the second column by the length of W2, and so on, right? But if you divide each column by the length of its column vectors, what you are going to get is that, okay, you are multiply. For example, let's use W1 as an example. Then we are trying to divide this thing, right? But if you want to keep the multiplication the same, okay, maintain the same multiplication result, pretty much this part, original is 1. It now has to be changed to W1, the norm of W1, right? The length of W1. Otherwise, then you multiply this one to this one, you get W1, right? Right? Okay, same thing apply. So this part, okay, you need to multiply this whole column by the length of W2. You need to multiply by length of W2, which will make the this diagonal position to be W2, the length of W2. Okay, because here you will have to you have to divide this W2. You need to divide it by the norm of W2 because you want to make this Q, okay, matrix, okay, to be, to consist of like the column vector that are orthonormal. So you need to divide the length, okay, of their column vectors. So these vectors will be added, will be multiplied to the column, each column in this diagonal matrices, and which, okay, still will guarantee, okay, see, the R is the upper triangle n times n matrix. It remains to be n times n upper triangle, and original is diagonal, and if your Q is also orthogonal only, then your R is like the diagonal position will all be 1. But no, because like you are multiplying each column by the length of like wi. Okay, so the diagonal entries are, you can only guarantee they are positive because you are multiplying each column vector by a length, which must be positive, right? Okay. So that's pretty much about it. Okay. So that's like you know, the concept of like Green-Smith QR factorization. This is something new in this section. Okay. In other words, you can sort of represent the whole process, or like capture the whole process by the matrix factorization. Okay? So then, okay, let's consider this example. Okay, so compute the Green-Smith QR factorization of the matrix. Okay, yeah, I mean, first, of course, you have to show that the column vectors are independent, or their rank of this matrix is 3. But let's, you know, yeah, let's just skip this part. Okay, and then, okay, remember, this is your A, right? And then you can compute, okay, the orthonormal basis out of these 3 column vectors. And the first you know, vector, the first column vector in the resulting orthonormal basis would be this one, right? A1. But of course, like you need to divide the length of this vector. So you can see that, okay, it's 1, 2, 2, 4. So you can see 1, 2, 2, 4 divided by 5. Why do you divide it by 5? Because 1 square plus 2 square plus 2 square plus 4 square is what? 1 4 4 9嘛，9 4 16 9 plus 16 is 25. Okay, square root of 25 is 5, right? So you divide like this each component by the norm, okay, or the length of this column vector, which is 5. So it's the result is this one. And this one you can see the diagonal component is 5. That's the length of this column vector. Okay. And then, okay, then you need to do like sorry. Okay, maybe this one will work. Okay. Then W2 will be, okay, V2, which is like, in this case, it's A2. Okay, the second column vector, okay, minus what? Okay, it's like what's it? A2 dot W1, which is actually like A1, the same direction, okay, and then divided by the length of A1 multiply A1. I mean, or put it another way, this is U1. This is U1. Okay. Let me double check. U1, yeah. V2 is A2. A2 times, it should be U1. U1 times let me double check. W2 is this one. W1. Let me see. Let me just use W1 is A1, right? And A1 square should be A1, and then A1, yeah. Let me just follow this notation in order not to get confused. So then we plug in. A2 is what? -2, 0, -4. 0. Minus. Okay. A2 dot A1. -2, -8. So -10. And A1 dot A1. A1 dot A1 is 25. We know that. Times A1, which is 1224. But, okay, what we are going to do is that, okay, we need to put this thing to the other side. Okay, so W2, so it's going to be like this one. A2 is going to be W2 minus, because this is already plus. So this is 2, 5. So minus 5/2. And this is like, A2. Okay. So that's going to give us like minus A2 is W2. Okay. So you can see that that's A2, right? And then, okay, let me see. Wait. This is A1. This is A1, not A2. And which will be, and we know it's A1 is the first one. It's U1 already. So basically, okay, this computation, okay, if you decompose it, okay, this one will be your W2, okay, divided by length, okay. You can see that it's one, yeah, the square, okay, you square every term and add them together. It's also you also get like a unit length. Okay, so this is length 1 column vector, and it's going to be like -2, 4. 4 is going to be the original length of your W2. Okay, and then you need to that's where you, because you, that's original is A1, and this A1 divided by 5 is your U1, right? Okay, this is what you get. This is A1. This is A1 divided by 5. So this is U1. So you can see you have -2, okay, term here. So -2 here. And this is, as I said, this is like the length of this vector. And you can keep doing that for the third column vector to get the whole result. So basically, you can see this one, okay, each column vector will be will have like this, the unit length, and they are orthogonal. Okay, so they are. This is like they form an orthonormal basis, and this one will be upper triangle matrix. Okay, so this is Q, our Q. This is our R. Okay. So that's it for this chapter. Okay, and we are not going to cover section 7. Okay, orthogonal polynomials. Okay, we'll skip that section, and we will talk about matrix. Used in the polynomials. In the next chapter. Okay, hopefully, but not probably not today. So, oops. Okay, so let's take 10 minutes break. When we come back, we'll continue to talk about the chapter 6, which is the last chapter. Okay.